Okay, in the previous lecture, we discussed about the binomial distribution, and these are the characteristics of a binomial experiment, basically, or a binomial distribution. So the binomial distribution is applied to a discrete random variable. So take note, it is a discrete random variable. So each repetition of your experiment is a trial of your binomial experiment. So the results for each trial is just one of two possible outcomes or events. So it's either success or failure. So in other terms, it's either your desired outcome or your undesired outcome. And the probability of the two possible outcomes or events remain the same for each repetition of the experiment. So again, the probability of each outcome, whether you want it or not, is consistent. It's a constant value. And the trials are independent of each other. So the binomial formula is the probability of a certain number of successes if you conduct a certain number of trials is given by this formula. So we already talked about this one previously. Now, how about we apply the normal distribution curve for our binomial experiment or our binomial distribution? Now, there's a caveat for this one. So, since this is a discrete value, so the binomial experiment by itself is actually applied for discrete random variables, and a normal distribution is technically for by itself is a continuous variable. So how do we actually calculate it? First, you must have a certain characteristics or certain criteria for a normal distribution to be used to approximate. Again, this is approximation, not the exact value. This you must your trials, your binomial experiment must have certain criteria, must fulfill this criteria in order for you to apply the normal distribution curve in your binomial experiment. So, and that criteria is having the value of NP and NQ is greater than 5. So it's basically a constant number of 5. So that means you must have a large number of n, because remember, P and Q are probabilities. So they range from a value of 1 to 0. So mostly these are in decimal, so less than 1. Usually it's less than 1. So you must have a high number of trials in order for your binomial experiment to become, or for you to apply the normal distribution curve for your binomial experiment. So this is a table of the binomial probability distribution for 12 experiments or 12 trials with a probability of 50% for the success and 50% for the failure. So you have here the probability of getting X. So this is from binomial probability distribution. This is in our table previously. I have to scroll a lot. But anyway, it's in our table. Binomial distribution table. And it's not loading. Anyway, so going back, so we now have this probability. So from the binomial probability distribution for 12 trials with a probability of 50, first let's check, is this applicable? So P is 0.50, that means the undesired outcome is also 0.50. Because again, 1 minus 0.50 is equal to 0.50. So 12 times 0.50 is 6. 12 times 0.50 is also 6 for Q. So NP and NQ is both greater than 5, so this applies to your probability. So that means that for your binomial probability, for you to use the normal standard normal distribution curve for your binomial experiment, you need to have at least 12 trials for a success chance of 0.5. So if your success chance is 0.6, you must have a trial of, say, greater than 12. So that's why, because the scenario is both NP and NQ is greater than 5. So if your probability of success, which is P, your P value is 0.6, that means your Q value is 0.4. So N times 0.4 must be greater than 5. So what is, what's it? 80 trials? So what is that value? So 5 divide 0.4. So you must have 13 trials. If you have the probability of success is 60 and the probability of failure is 40%, so around 13 trials. So the minimum number of trials, this is already for the 50-50% chance for a binomial probability is actually 12. So as your chances of success increases or the chances of success decreases, you need to, or rather, if you the more that you go away from the 50-50 probability, the more trials you would need to have. So anyway, this is the histogram for the probability distribution for this table. So let's look at an example. So according to estimate, 50% of the people in the United States have at least one credit card. So here, your desired outcome is having at least one credit card, and the probability for that is 50% or 0.5. So if you randomly sample 30 persons, what's the probability that 19 of them would have at least one credit card? So our number of trials is 30. Our desired number of successes or favorable outcomes is 19. So that's our x. So if let's actually check. So NP and NQ must be greater than 5. So N is 30 and P and Q is 0.5. So 30 times 0.5, that's 15. So we have a good, that's much greater than 15. Sorry, 5. And then we have, if we are going to apply the formula for the exact probability formula from our binomial formula from previously, the answer is 0.0509. Actually, it's not really required that we need to apply normal probability distribution, because again, normal probability distribution only approximates your binomial distribution. This cannot give us the exact value. We can actually have this formula to help us for probabilities of binomial distribution. We only do that when this is actually applying the normal distribution or standard normal distribution curve is an alternative way when we do not know certain variables for our experiment. So this is the alternative way. So using your standard normal distribution, and NP and NQ requirement is 15, so it satisfies the greater than 5 requirement. So the next one is to know what is the standard deviation and the mean, population mean and population standard deviation. So we can get that by calculating the sigma standard deviations NPQ. So this is our standard deviation, and our mean is NP, or n mu is equal to NP. So that's 15. Now, the thing here is to convert our Q, or rather to convert the X values. Because of course, for standard normal distribution, we need to have the X and then convert it to Z. But how do we get the X values? There's a continuity correction factor. So to get the values of X for the normal distribution, we need to add 0.5 or subtract 0.5 from the value. So basically, at the right side, or the maximum value, we add 0.5. At the minimum value, we subtract 0.5. So this is the correction factor. So why? Because again, the binomial distribution is in fact a discrete probability distribution. So you don't have this smooth curve, but rather you have this histogram. And for histogram, you have actually steps. So this is not a smooth curve, these are steps. So the plus minus 0.5 is actually the correction for the smooth line, the areas between the curve. So the how should I say this one? If we look at this one, if this is the normal curve, so if you notice, you have the step. So you have blank areas here and also blank areas here. So that's the 0.5 correction for your distribution. So going back, so you need to have plus minus 0.5. So going back to our equation, so X is 18.5, because again, the problem here is 19. What's the probability that 19 of them will have at least one credit card? So 19, since the approximation here is minus 0.5, at least 19. The question is 19. Where is it? Okay, the question is at least 19. The probability of them will have at least 19 of them will have one credit card. So the value is 19. So which is actually a single point. And so we have here 18.5. Where is it? So 19, the exact value is 19. So because this is a histogram, 19. But for an interval, it becomes the values flanking 19. So that's 18.5 and 19.5. So plus minus 0.5. So 19 plus 0.5 and 19 minus 0.5. So that's your correction factor because this region is 19 for a discrete distribution, but for a continuous one, it must be a certain interval. So the interval is 18.5 to 19.5. So plus minus 0.5. So the x values are 18.5 and 19.5. Convert it to z and then get the area of the curve from 18.5 to 19.5, and you will get 0.0498 or 4.98%. So if we compare it with the exact value of the distribution, that's 0.05. So you have an error of 0.01 because again, this is approximation. So the normal distribution can only approximate your binomial distribution. So let's look at another example. So according to survey, 32% of people working from home said that the biggest advantage of working from home is that there is no commute. Suppose that this result is true for the current population of people who work from home. What's the probability that a random sample of 400 people who work from home, 108 to 122, will say that the biggest advantage of working from home is that there is no commute? So you have your 400 people, 108 to 122, an interval of between 108 to 122 people will say that no commute is the best advantage out of 400 samples. So it's basically an interval value of 108 to 122. So the probability for a favorable view of a favorable outcome, the outcome that you want is that they would answer that the biggest advantage is no commute. So 32% is the probability for that. So the P is 0.32, that means your Q is 0.68. So since the NP will give a lower value, let's first check, would our NP give a value of greater than 5? So NP is greater than 5, that's 128. And this is actually also the mu or the mean, the population mean. That's 128. And the population standard deviation is calculated from formula. So this mu is equal to NP and sigma is equal to square root of NPQ. These, remember, are the mu and standard deviation calculations from our binomial formula from the previous lecture. So we calculate the mu and the population standard deviation. Now the intervals is 108 and 122. Right? 108 and 122. So apply the correction factor. 108 minus 0.5, that's 107.5, and 122 plus 0.5, so that's 122.5. So that's our x values. We get the z counterpart, so that's negative 2.20 and negative 0.59. And then we look at the curve. So the area beneath the curve at the interval of negative 2.20 to negative 0.59 is this value. So the shaded area is 0.2637. So this is 26.37%. And that is the probability of when we ask people, randomly ask people, we randomly ask 400 people who work from home, and the chance that 108 to 122 of them will say that the biggest advantage from working from home is this one, 0.2637 or 26.37% chance of getting the 108 to 122 of them will say that you will get your desired outcome. So that is the binomial distribution. So it doesn't mean that 26.37% of the people will tell you that their biggest concern is work from home, but rather there's a 26.37% chance that you would get a number of people, 108 to 122 people that will say that you have a that your favorable outcome, that is work from home, the favorable outcome, sorry, is no commute as the biggest advantage. That will be the biggest advantage for them. So the number of people that will give you the answer, or rather, you will get 108 to 122 people that will answer that commute is the best advantage. Is the probability of getting that amount of people is 26.37% chance. So let's look at another example. So in a Pew Research Center conducted on a certain day, June 3 to 17, 2019, US adults were asked if they knew what net neutrality was. Of these adults, 45% know that their net neutrality refers to the principle internet service providers should treat all traffic on their networks equally. So what's the percentage is true for the current population? So what's the probability of 326 or more adults in a random sample of 700 US adults will know that net neutrality, they know what net neutrality is. So applying this principle, again, NP, that's our mu, and also it's 315, is also greater than 5, so we can apply the normal probability here. So NP is 315, mu is 13.12. So the thing here is 326 or more. So it's from a value of z greater, the area is z greater than or the probability from that is greater than 326. So applying the correction factor less 0.5, because the at least 326 here. So you have a minima, but no actually maxima. So at least 326. So 326 minus 0.5, that's 325.5. So that's our x. That's a correction factor. So it should not be 326.5, but rather 325.5, because the question we are looking for is 326 or more. So 326 is the lower limit. Now, if we are looking at 326 or less, or a maximum of 326, 326 now becomes the maximum limit. So our x becomes 326.5. That's when you would add the 0.5. But the problem states that it's 326 or more. So the lower limit is 326. So it's 326 minus 0.5, or 325.5. That's our value for x. And x, convert it to z, you get 0.80. So look at our shaded region. Since 325.5 or more, or rather 0.80, that's from the 0.80 to the right. So since again our table will give us values to the left, we just subtract it from 1. So the value to the left is 0.2119. So that means that in that test, so if basically the 0.2119 or 21.19% probability means that you will get, if you conduct this test for 700 adults, if you ask 700 adults, there's a probability of getting the probability of, or rather you have 21.19% chance of finding 326 adults out of 700 that knows what net equality means. So it's not the percentage of adults finding of you finding adults that knows net equality, but rather of you finding 326 adults that know net neutrality out of 700. If you ask 700 people, or out of a population or of a sample size of 700 respondents. So that is your binomial probability distribution, or rather applying the standard normal distribution to your binomial probability distribution. Okay, so that ends this part of the lecture.